the added mass times the acceleration, normal acceleration at the half-chord point as a function of time, in instantaneous response. This instant acceleration gives you this instant lift. But this was not complete. Why? Because because the tangential velocity at theta equals 0 was not 0, was this guy. So it's not 0, it's finite. So he introduced the circulatory part to make up for that. For the circulatory part, here is the cylinder, we have a vortex here, and whenever you introduce a vortex, it's immediately of unknown strength. Whenever you introduce a singularity, any singularity, then he introduced another singularity here to satisfy the law of zero total circulation, so they are the same. Not to disturb the no penetration boundary condition, this dictated a certain distance for this guy. Then how to get this gamma? Because this v theta was not satisfying the Cotta condition. Now we can use the Cotta condition, which is v theta non-circulatory at theta equals 0 plus v theta circulatory at theta equals 0. This has to vanish. This guy was the negative 2 v 3/4, and this guy was 1 over pi b integral from v to infinity gamma wake of z and t square root z plus b over z minus b dz. This is 0. This is your integral equation for wake circulation, and you can see here the integral from v to infinity. Okay? And just reminding you that there's plus here. This guy, the multiplication of pi b times this guy is the quasi-steady circulation. So you can view this as 3/4 chord angle of attack or velocity at any time is the forcing input to your aerodynamic model, or the quasi-steady circulation. Of course, I prefer the latter. Could not solve this integral equation for any arbitrary kinematics. Had to introduce harmonic motion, and then the Bernoulli equation gave us that the circulatory lift is rho u times this integral from b to infinity gamma wake z divided by z square minus b square dz. So you can write it as, from here also, as rho u gamma quasi steady times the ratio of integrals, and this ratio is simply the c of k, right? So this is Tudorson in a nutshell, the approach of Tudorson. So this is the governing equation, the integral equation for wake circulation. Where it came from in Tudorson's approach is from the Cotta condition. Okay. Let's remember together what we did last time with von Karman and Sears. So no division into non-circulatory and circulatory, just right away. So because it's right away, we know that if it's an unsteady flow, I have to account for wake. So let's introduce a wake singularity, and like I said, whenever you introduce a singularity, it's unknown. So they added this circulation, right, to satisfy the law of zero total circulation. So together they maintain the circular streamline, and it also dictates the location of this guy. So we can get v theta, that's fine. But v theta at theta equals 0 is also not 0. So they added gamma cotta here, right? Such that v theta total at theta equals 0, this is 0. Now we got the value of gamma cotta, and still this guy is unknown. So from the v theta total, we can divide this by 2 sine theta, it's a function of theta. This gives you the u on the airfoil, which is related to the circulation distribution as half gamma. So this is the circulation distribution over the airfoil. It's a bound circulation. Von Karman says called it gamma 1. It's a bound circulation, but due to the wake, due to this gamma in the wake. So this is the bound circulation that is due to wake. So in steady flow, this should be 0. Okay? And then in particular, we can get its gamma 1, which is the integral of negative b to b gamma 1 of x dx, right? So this is the total bound circulation on the airfoil due to wake. Bound circulation due to wake, right? Then I said, okay, the problem now is set up, but we did not satisfy the most important condition, which is your motion. So the no penetration, well, we can always satisfy it in a steady fashion. Just do it steady. So we have gamma naught and gamma naught, bound circulation and bound circulation due to the motion of the airfoil, due to a camber. Thin airfoil theory, pure steady thin airfoil theory. So now we have, what do we have? We have gamma naught and gamma 1. This is bound circulation over the airfoil. Due to airfoil motion, directly, steady version, and effect of the wake. So if you add to this gamma wake, this is the entire circulation in the flow. This should be equal to what? 0. And this immediately gives this here, which is the law of zero total circulation, conservation of circulation. It immediately results in the exact same governing equation, exact same integral equation for circulation. Okay? Then they get the loads in a different way. They didn't use the Bernoulli equation. They used the impulse, the vertical impulse, due to a distribution of vorticity or circulation. It's just the summation gamma times x, gamma I times xi. Of course, they did it in an integral sense. Okay? And the lift is related to this impulse as the negative d by dt of the impulse. So they did not use the Bernoulli equation, but of course, because it's the very similar formulation, or within the spirit of potential flow, within the framework of potential flow, they ended up with the exact same Tudor's function and Wagner function. So this was von Karman series last time. Any question about that? So you can see here, Tudor's arrived at this guy from the Cotta condition. Von Karman series arrived at the exact same equation, but not from the Cotta condition. It's from the conservation of circulation. So you can do it whatever you like. Today we introduced Schwarz, so let's summarize Schwarz as well. So here in the cylinder domain, this is what Tudorson did. He worked in the cylinder domain, divided the flow into non-circulatory and circulatory. Here it's again in the cylinder domain, but no non-circulatory and circulatory. Schwarz did not work in the cylinder domain, it's right away in the plate domain, and did not also divide the flow into circulatory and non-circulatory. It's very straightforward. This is your gamma bound of x, and here is your integral equation gamma bound. This is the no penetration boundary condition, right? So this is zeta or whatever x prime dx prime over x minus x prime, and this is equal to your v motion of x. Right? This is exact same equation for thin airfoil theory. If you want to do it unsteady, then this means that your v motion is a function of time, which immediately dictates that gamma bound is also a function of time. If you stop here, this is quasi-steady analysis. You have to add wake. And if you have wake as a function of x and t, then you need to add its thing here, gamma wake. Okay? What they did is harmonic motion from the beginning, so no t anymore, right? then we need a relation between gamma wake and gamma bound. Well, the law of zero total circulation can give it to us. So conservation of circulation gives you that U gamma wake at B and any T is negative gamma dot at T. Very well known relation that we may criticize later, but anyway. So we got gamma wake in terms of the total. We got the gamma wake distribution in terms of the total bound circulation. If you put it back, now we have an equation that looks like negative 1 over 1, 1 over 2 by gamma bound of zeta, d zeta, eta, eta, zeta minus eta equals some function of zeta. Use Sohngen inversion formula, right? To get gamma bound, but there is an unknown. But it's not a new unknown. Why? Because this guy is the total amount. This, right? So gamma bound is negative 1 to 1 gamma b zeta d zeta. Immediately gives you gamma bound. We're done. Okay?